Okay, the next speaker is Antal Jevicki, and he's going to tell us about bulk and Witten rules in bilocal holography.
Okay, thank you. I'm very glad to be here. I'd like to congratulate Johanna for such a nice, excellent meeting with physics, surrounding, and wine. I'm still waking up from yesterday, so I apologize for misspelling. Is it fine? Sometimes it's the other. Then it's okay. Oh, okay, that's it. Okay, the topic that I'll be discussing fits into this gauge gravity duality, but gauge should be replaced by vector models. So it's a subclass of dualities called termed vectorial duality. To that, we have developed an approach which was termed holography from collective fields, which Shumi does some time ago. And in a way, that is a framework or a scheme to construct the bulk theory from the original field theory. And some parts of this we have done during these last several years with some of my students. In a canonical picture or some spinning particle picture. But the present talk, I'll be discussing some recent calculations on bulk equations which follow from this scheme, and also Witten diagrams which we like to exhibit their form in this scheme. This is work with two of my former students, Yoongi Yoon and Kenta Suzuki, and Robert de Mello-Koch. And the paper should appear as soon as we have a factor of 2 clarified. So let's see. Just that so the framework is fairly general, and it covers models across dimensions. And maybe it will be useful that I'll point to some models which one can study and get insight into the duality which they produce. D equal 1, that's the SYK, which was heavily studied in the last 3 years. Tensor models, even though they are not vector, they have a subsector which is vector-like. The same for the minimal models and ADS3 higher spin theory. And the classic case is obviously this vector in 3 dimensions, which again has been studied a lot, being dual to Vasiljev's higher spin theory. I'll just point to even one other model, which I randomly picked up, is the Fishnet matrix model of Kazakov, which he has been developing with collaborators recently. I'll maybe make a comment on it. So this is a class of models where what I say might apply. The question marks, I'm not sure if someone can guess why red and black. The black and red question marks. The red one those are the cases where the dual theory is not known at all, maybe meaning we don't know what the dual theory is, and then the framework which I'm describing is a candidate of studying that dual theory. The black is where the dual theory is actually known, but the action is not known, which again relates to the topic I'm discussing, because I'll be talking in terms of an action, and therefore it will be a candidate for an action. Let's see. The idea is brutally simple. It's just the statement that invariant bilocals for these vector theories, which is really everything, those are really all the invariant operators in the theory, contain the information about the bulk, and that there will be this bilocal, which will be in a correspondence with higher spin fields. Here there is a sphere for spin. I will explain that. it will be a statement of one-to-one correspondence, meaning that this field of dimension d plus d is d plus 1, which is ADS, and obviously the sphere should be d minus 1, and that will also fall into place. So just to spend a couple of words on what do I mean by this higher spin theory on ADS and the sphere. Usually higher spin theory would be described in terms of a sequence of fields with indices, tensor indices, which are symmetric and traceless. So even in linearized case, it's a fairly complicated set of equations to follow. But I refer to a version which would be a physical version. So a physical version would be familiar to experimentalists who do gravitational waves. They certainly would not care about indices. They have no interest in indices. So the physical version is this comes with a gauge. In this case, for example, the Donder gauge and the tracelessness condition. You should imagine solving those gauge conditions, analyzing what the solution to that is, and then there would be a reduced field. For example, in d equal 3, so we always have ADS, but the index structure would be packaged into an angle, and that's basically sum over one remaining polarization, and that is really the notion that is the notion of this reduced higher spin. And when I make that statement that we are mapping one into another, that's what I mean. That will be the version, the physical version of higher spin theory. And the correspondence is stated to be very direct or explicit, meaning that it turns out that it is a correspondence which can be stated in momentum space in Fourier transform. Very easy. You Fourier transform the bilocals. You Fourier transform the ADS plus, yes, that angular degree of freedom packaging the spins. And the statement is that this is actually equal to each other. So the higher spin dual field is equal to the bilocal field. There is a change not of coordinates, which we actually tried first. You first try to change coordinates, doesn't work. But changing momenta, it does work. And there is a very clear reason for that. For example, in d equal 2, which I already mentioned, this would be the correspondence between the change of variables in momentum space, and this is a very elementary example of holography exhibited explicitly, meaning that this is a change of momenta from the bilocal momenta. We are in Euclidean space, so these are just Euclidean momenta. This is the center of mass, obviously, for ADS. The z direction, that would be the difference, really, with a negative sign, so that dz, and then the emerging spin direction, it is right there. So the statement is that there is such an elementary correspondence between the dual high spin field and this bilocal field. So that in a way is why we were. The reason for that, I think I will have to go, is the way you come up with this formula, even though it looks rather simple, even that took several weeks to figure out. It has to do with identifying the realization of conformal symmetry on obviously, conformal symmetry is very easy. 2 copies of conformal generators on the bilocal, inherited from the local field theory, and the realization on that physical higher spin theory, and that is some non-triviality. That's why that reduction to the physical degrees of freedom has to be worked out. That is the one which produces this formula, how is conformal symmetry realized on that physical space. And then you can attempt this comparison. And the reason for momentum space is also visible if you look at these realizations. It allows for change of variables in momentum space, but not in coordinate space. Anyway, that was kinematics, and here is the full nonlinear construction. So the proposal is a fully nonlinear, and it is specified just by one thing, an action, which historically we called the collective action. This is an action which summarizes all the information about large N. N appears everywhere in this action. First of all, that is the classical action. Trace log psi of that bilocal, that is, you might think of it as some kind of entropy. I will not elaborate more on this action because I will soon be doing calculations using it, so maybe that will illuminate its relevance or usefulness. So in a way, for that case of Vasilyev's, when one says that there is no action for higher spin theory, this is a candidate. This is an action which is an action for physical degrees of freedom of higher spin theory. 1 over n is the coupling constant. And you proceed in the standard way. There is a background solution, which is the expectation value of the bilocal, and the correlator of the local. And then you expand that in perturbation theory. And that would generate you the 1 over n expansion. So it's a very standard procedure. Once you expand, you should take into account that this bilocal is really a matrix in that bilocal space. So all the products are really star products in this matrix sense of a bilocal. That's the only comment on the structure of vertices which come out of that action. But the vertices are just the geometric series coming from that trace log. That specifies an infinite, obviously it's non-polynomial, so that is an infinite sequence of vertices. And that is all. This theory, field theory, which is, you can think of as some kind of analog to string field theory, which has a similar structure of a star product. This field theory is then the candidate for describing all those models that I summarized in various dimensions. In a way, it is universal, which is very nice. And here is maybe now after this introduction, I can begin to do some of the calculations, which will help you understand what it does. Obviously, the quadratic term, which comes from a Laplacian. This was this background, which is shifted. And I'll be often considering just simplest free scalar theory, lambda equals 0. For example, if you work that out, you will see a fourth order in derivative Laplacian, which is associated with this bilocal theory. It is not d1 squared plus d2 squared, which you would expect, but d1 squared times d2 squared, which you might be a little bit surprised. And then the form that in terms of the conformal generators, it is the C4 Casimir, which this Laplacian is. This will have some relevance on the question of locality, ultimately, of this theory. So this is the simplest example. I will mention some further examples. But then you proceed again in the standard way. You have two bases to expand in. One is the natural Cartesian basis of the bilocal. That is one set of eigenfunctions, and you can build a propagator that way. Or the other is the SO2D minus 1 basis with those eigenfunctions. So here is just an example in 3 dimensions. And we evaluate the eigenvalue of that Laplacian. That is actually nice, since I already emphasized momentum space and that there is something going on in momentum space. This is the wave function in momentum space, the set of eigenfunctions, which looks fairly reasonable. I should mention that studies of CFT in momentum space, we learned a lot from the paper by Skenderis et al. Some things are nice, but there are many other, when you go to study correlation functions, things get interesting. This will be the cubic vertex. I'm just writing it so that you see that it's a set of delta functions. There is nothing else going on except that star product that I emphasized. So I will not spend time on that. Since I emphasized the map, which is that double Fourier transform, you Fourier transform to momentum space, then you Fourier change variables, then you Fourier transform to ADS space, you can ask, what is the ADS Fourier transform version of that Laplacian, which I mentioned before for the free example? So here is the Laplacian in ADS. It is a standard Laplacian. These are the spin degrees of freedom in that example of one of d equal 2. And then there is another, so it's quartic. This quartic form transforms into that quartic form by that Fourier transform. This features a set of eigenvalues which are physical. Those are the highest spin currents in that model. And this features a set of eigenstates which actually should not be physical, meaning there are no currents or dual things expected to be in the spectrum of this higher spin theory. So that decoupling in calculations of diagrams is fairly relevant later on. But this is one example. The Fishnet model, where Kazakov and all study operators of this kind, traces of matrices phi x1, phi x2. They identified a set of diagrams. They diagonalized the spectrum of for this operator. They found this formula, which is just summarizing their result. This is again quartic in the conformal. So they do not know what dual this is. They don't even know whether it's ADS space in a sense. But if I translate into this bilocal description, it would be just a deformation of this previous Laplacian. So this would be the next, well, that was the simplest example, the simplest case of duality I can study. And this would be the next simplest case. You just deform it by a mass term, even though you wouldn't call that a mass term. So the Laplacian in ADS would be, again, that product of two Laplacians and just deform it by an extra term. So that is the Fishnet model. The SYK model is even more interesting. You remember my collective Laplacian had this term. This is really just a copy of the phi fourth theory. You should replace this by phi 0 here and phi 0 there, then and have it in one dimension. That's the Laplacian of the SYK model. And if you translate it into ADS by that map, in this case we have an infinite product, so it shows you the complexity of the SYK model. It's not the product of two Laplacians, and all those particles are physical. There is a sequence of growing masses with this quantization rule, which is still a mystery of what dual and why would that quantization condition appear. But this is the summary of what the picture you see after this transformation in the SYK model. So these are the examples. Now I can just, the rest is, I think I should have 10 minutes. Oh, okay. 5 minutes, but you'll be happy maybe that it's only 5 minutes, because the second thing is just the calculation. The calculation was inspired by a calculation by Beckhardt and Johanna and Ponomarev and Slate, done 2 years ago, where they studied processes in ADS and also constructed ADS cubic and quartic vertices. That was the major study they have done. So it's interesting then to compare what do you see in this scheme with these vertices, which are here, quartic and cubic. And I should just say, obviously, the diagrams are very obvious. A couple comments. You can compute correlation functions of the bilocal, 4-point correlation of the bilocal. Bilocal generates all the currents. So once you compute that correlation function, then the correlation functions of currents automatically come out. They are just derivatives of the previous ones. There, in this scheme of bilocal field theory, there will be 2 ways to do the calculation. There are 2 bases, which I already emphasized. One basis is the Cartesian bilocal basis, X-base, CFT basis in a way. And the second one is the CPW basis of conformal partial waves. You can calculate in the same quantity in either one of those bases. You will get different expression, and in a way you will that way deduce some identities which are known in expansion in partial waves. So this will be the propagator, but I don't have time. Just to emphasize that in the bilocal basis, it's sometimes very easy to calculate, in particular in this free example, because the structure of the vertices and the propagators is such that there is a cancellation between, in all those expressions you see in phi 0 and inverse phi 0, and obviously that might cancel. So it's very quick to see that you are getting the answer of correlators known from CFT. That is very easy to see in the bilocal basis. If you pursue the calculation in the conformal partial wave basis, here is just some detail which you might appreciate. There are formulas which are leading you to an expansion expression in terms of cross ratios. And then you get this kind of formula where you get an integral over conformal blocks where poles have to be picked up. The non-trivial part actually is the discussion of poles in such an expression. This was an S-channel exchange diagram. There is the physical pole S minus 1 half. I already emphasized this from my propagator. There is the unphysical pole at S plus 3 halves. It turns out its residue will be 0 when we pick up that pole. So that is that statement that even though the Laplacian is quartic and product of 2 ADS Laplacians, there is an unphysical branch which is projected out. There are other poles which have to be tackled, and I don't have time, neither do you want me to discuss all the other poles this has, which then cancel, and you find the result, which obviously I said you could, this is the example of the free original theory. So you know the answer, which in this case for that diagram would be just these two pictures with a scalar propagator running around here and cross. This is known as A and B in some version of a standard notation. These are the these are the operator product coefficients. And this is an expansion then, which you obtain. In our case, this basically is an identity, since I found the result in one basis to be this. and in another basis to be that, we proved an identity, and there are many other identities you can prove that way. But now I can just finish by comparison with that work which I mentioned by Beckhardt, Erdmanger, Ponomarev, and Slate. They have done, as I mentioned, the same calculation in ADS, and the structure of, when we compare, is obviously very, very close. There is maybe just a small difference when we look at the contribution, where did the contribution come from. In their case, BEPS, thanks to Johanna, it's not BPS. So there are contributions in their case from single traces and double traces. In the bilocal, it's natural, because that's the spectrum of that field theory, that we have only contribution from single traces. So there are comments I could make on non-locality, which is another topic related to this investigation. But let me just conclude. Several of these calculations just showed that this bilocal field theory can be taught pretty well, especially in the structure of diagrams, as an actual field theory of this higher spin gravity. Loops, there is no issue with loops. The loops can be calculated. In fact, the fact that it is the physical set of fields means that you do not need any ghosts. So just as well, for loops, this is a very convenient description of the theory. And it's a little bit less convenient, but nevertheless, you can study classical non-perturbative solutions, and that is being done by Maldacena in the case of SYK. So there are probably some further interesting things to be studied in this framework. Thank you.
Thank you. Any questions?
So can you just elaborate a little more on this, or summarize the locality properties now? What did you find? I mean, also in comparison to what we did.
So non-locality, from that study of, and earlier studies, I think that was, it was concluded that the 4-point vertex is non-local, and in fact non-local in this sense that it contains inverses of ADS propagator. So as you probably could see, that the vertices that I wrote are essentially delta functions for this joining of bilocal. So this was, maybe I called it a no-go statement. I'm not sure whether it's a theorem. There's obviously some assumptions. So obviously this bilocal theory avoids some of the assumptions. My kinetic term is quartic, which obviously is one in those theorems. So it's very easy to avoid the theorem. In that might be one reason, but there might be other reasons which has to do with these poles and contribution of single trace and double trace operators. So I'm not sure what is the reason that we are able to avoid this no-go theorem. There might be two different sources of that. Okay.
Any other? Yes.
So do these unphysical poles correspond to gauge degrees of freedom in the harsh spin language?
Those are interesting things because at one loop, for example, you will receive some anomalous dimensions in some 1/n corrections. So I mentioned loops. And in fact, it is like getting masses for higher spins. Then this would be some actual physical Stuckelberg field, which is appearing in this way. So there is some potential use for those, but not in this massless limit.
Okay.
So, excuse me, you have this high derivative kinetic term. Do you have any physical interpretation for why it should be the case? Why it's not canonical to derivative?
I don't think you can expect anything. There is no predisposition. So what the kinetic term comes after shifting by a background, we work it out. And yes, we're a little bit surprised that it's not C2, the second Casimir, but it is the fourth Casimir, but that's what it is. So I don't have any other insight. There is some insight we got into that from a spinning particle perspective. It is also natural for a spinning particle. If you remember a regular relativistic particle, it would be p squared plus m squared, which is a constraint. For a spinning particle, that would be a natural constraint. So there is some reason for it from the spinning particle viewpoint.
Okay, let's thank Antal again.